Hello students, we're moving on to the next big topic in this class, and that is momentum. Now before I get into momentum, I want to make a couple of comments. First of all, this book presents momentum in a way that is a little different from the way I'm going to present it. And the way the book does it is fine, and the way I do it I think is pretty good, but they're not the same. And so I really do need you to be reading the book and studying what it has to say, and then putting that together with what I explain. I think you're going to get a nice complete picture of this topic. Now, momentum was something that Isaac Newton actually figured out. He didn't figure out energy. And so in the history of physics, you had Newton's laws, and then there you have momentum, and then a long time after that, there's energy. And so a lot of books will follow the historical sequence. They'll introduce momentum first, and then they'll introduce energy. Our book did it the other way. I'm not exactly sure why, but that's fine. Okay, so let's talk about momentum. So Isaac Newton called momentum the quantity of motion, which kind of makes sense when you look at what goes into calculating momentum. The symbol for momentum is P, and to get the momentum, P, you multiply the mass of whatever it is that's moving times its velocity. Velocity is a vector, so it has a direction, and consequently momentum is a vector. It has a direction too. If I write P without the little vector sign on top of it, that means we're talking about the magnitude of P. Okay. The units for momentum are going to be kilograms, that comes from the mass, times meters per second from the velocity. Kilogram meters per second. Now these units are equivalent to newtons times seconds. And this fact is going to be significant, it's going to be obvious actually, when we talk about impulse in just a little bit. All right, now let's look at some momentum examples. So way back in the 50s and 60s, the French Citroën was a really fancy deluxe car, and so I used it for this example. It was very sleek and streamlined. So this old Citroën with a mass of 1 ton is moving at 30 meters per second, and it's going to the right. What is its momentum? Okay, so it's just a plug and chug sort of thing. Its mass is 1,000 kilograms, and its velocity is 30 meters per second to the right. That's what the I hat unit vector is telling us. And we get our answer, 30,000 kilogram meters per second in the I hat direction. In other words, going to the right. Yeah. Okay. Let's have another example. I'm going somewhere with these examples. You'll find out. Okay, so we still have our Citroën with the same momentum as before, but now there is a 1.4 ton Cadillac, and it's moving to the left at 22 meters per second. What is the total momentum of the system? So in other words, by saying total, what I mean is if I were to take the momentum for the Citroën and the momentum for the Cadillac and put those two momentums together, I would have the total momentum. Yeah. So we already know the momentum of the Citroën, car 1. We're going to figure out the momentum of car 2 right now. It's its mass, 1,400 kilograms, right? 1.4 tons is 1,400 kilograms. And it's going 22 meters per second, but it's going to the left. So I put a negative here. And so, yeah, we still have the I hat. Now, I hat means going to the right, but we have the negative sign, so that flips it around. And anyway, we get our answer, negative 30,800 kilogram meters per second times I hat. Okay, but that's just for the Cadillac. Now we put the two momentums together, and we have 30,000, positive 30,000 for car 1, negative 30,800, that's for car 2. We put it together, we have negative 800 kilogram meters per second. So that's going to be to the left. All right, so the total momentum is that much, negative 800. Now, the two cars smash together. And let's say that they stick together. And let's say that the wheels don't lock up, and we can sort of ignore friction, just say, what's this wreckage going to do? Well, the fact that the total momentum is to the left here, negative 800, it tells us that the overall motion, right, as Newton would have said, the total quantity of motion, it's leftward. And so after the smash up, they are going to be going to the left. And not only that, but we're going to find out that there's this thing called the conservation of momentum law, and the momentum afterwards is the same as the momentum before, so it's still negative 800. And furthermore, we can divide by the total mass of everything, right, the two cars, and get from that the speed, the velocity of the wreckage. So the blob of metal will be moving to the left at 0.033 meters per second. So that's sort of a preview of things to come. We're going to be doing quite a few of these conservation type problems. All right, so that is a really quick introduction to momentum. Once again, the book takes a different approach. You really need to read what the book has to say. Now let's talk about impulse. So impulse, in physics anyhow, means a change in momentum. And our book happens to use the capital I letter. I will use delta P for the most part. And, later on, I is going to stand for electric current. So I don't really like using capital I because I know it's going to get used for something else. Okay, so delta means a change, and P is momentum, and yeah, so you and it is a vector, right? So we want to put vector signs unless we just care about the magnitude of it. So let's have an example. You have a ball, here it is, and it's not moving, it's stationary, and it has a mass of 0.4 kilograms, and you kick it, and they give it with an impulse of 16 kilogram meters per second. Now, we're going to get into the details of how the impulse happens, but for now, let's just say the ball is given an impulse of 16. What will be its new momentum and velocity? So start with the definition of change in momentum, delta P, impulse. So a change is the new minus the old. So we are going to solve for the new, right? It's asking what's the new momentum? And so we solve for that. We add the old to both sides, and we get that the new momentum is the impulse, the delta P, plus the old momentum. But the old momentum was 0 because it was at rest. So it's 16, that's the impulse that we were given, plus 0. So the answer is 16 kilogram meters per second to the right, okay? Yeah. And all right, so that gives us the new momentum, and we can figure out the new velocity because momentum is mass times velocity, solve for velocity, so the velocity will be the momentum divided by the mass, 16 kilogram meters per second divided by 0.4 kilograms. Notice that the kilograms cancel. We're left with meters per second, and we get the answer, 40 meters per second to the right. Wow, a cannon style kick. Wow. Okay. Yeah, and so here's a little note. I don't think you're going to see the symbol I for impulse very much. In our book, he's using it, but most books just use delta P. Yeah. All right, so where is delta P coming from? And so that's what this is about. So impulse is delta P, change in momentum, is net force times time. In other words, this is where that change in momentum is going to come from. It's going to be force times time. Yeah, so I mean, obviously, if you push an object, it will move. And if you push an object with the same force, but you push it for a longer time, it will move faster, right? It all makes sense with more momentum. And so we can write this simple formula. The impulse is the net force times the time interval during which the force is pushing. Okay, so let's have another example here. Your foot pushes that stationary soccer ball with a force of 800 newtons. So you see, there it is. We've got this force happening. And you got a little force sensor here, or a high-speed video, to kind of track these things. And the force sensor, the video, whatever, says that the push lasted for 0.02 seconds. So what will be the new momentum? So the new momentum is going to be just the change, right? The reason it's just this change is that we're starting out with 0 to begin with. All right, well, so that's going to be the changes, the net force times the time interval that the force is happening. Plug in our numbers, 800 newtons to the right, 0.02 seconds, and we get our answer, 16 newton seconds. And so now the units, newton seconds, right? These units are the same as these units. There you go. So there's something that to be pointed out here. Impulse and Newton's second law are almost the same thing, right? They all tie together quite closely. And so take a look at my notes, take a look at this, and see if you can kind of figure out what I'm saying here. And also, when you're doing the lab, I just assigned a lab to you on Pivot Interactives. You can refer back to this. There's a question which is asking you about this. Okay, so I think we should stop here. Thank you for listening and watching. Thank you for working hard and doing your homework. Yeah.